All right, friends, this is a re-recording of the 9 o'clock lecture for February 7th. It turns out that somehow in class I didn't click the record button properly, and therefore the lecture wasn't recorded. Last time we were talking about the Aldol reaction, which, as you recall, is the reaction of an enolate with a carbonyl compound. In this case, it's a self-aldol reaction, and the intermediate, we form the enolate with OH minus. The intermediate that's formed, the tetrahedral intermediate, has a negative charge on the oxygen. At that point, we ask, do we have a good leaving group? And the answer is no. So we wait until we wait, and then the negatively charged oxygen gets protonated by water, and we get to our aldol product, which is a beta hydroxycarbonyl compound, or alternatively, we go on to do the elimination reaction and get the alpha beta unsaturated carbonyl compound. And just to clarify, this portion of the molecule comes from the enolate, and this portion of the molecule was our electrophile or ketone. Today we're going to introduce a new reaction called the Claisen reaction, but you shouldn't think of it as a separate thing. In fact, it's just the ester version of the aldol. What do we mean by this? Well, if we take this ester and react it with sodium ethoxide, which is just sodium ion and the ethoxide ion, we're going to form a small amount of enolate, because the pKa for the ester alpha proton is so much higher than that of ethanol. We'll form a very small amount of ester enolate, just as we formed a small amount of ester in the aldol reaction. And then this enolate will attack another molecule of ester that's so far not been deprotonated. That attack generates, as we saw in the aldol reaction, a tetrahedral intermediate with a negatively charged oxygen. And just to be clear, we'll use the same labeling scheme. Now, as we compare that tetrahedral intermediate with what we had above, the difference is in the aldol reaction, there was no good leaving group on the now beta carbon, right? Whereas in the case of the Claisen reaction, or the ester version of the aldol, we do have a decent leaving group, at least a decent leaving group relative to the negatively charged oxygen. So basically we're comparing these two groups, and we're asking the question, is it reasonable for these electrons to kick down and for ethoxide to leave? Of course, if that happened, this would be the product that we get, but ethoxide would have been the leaving group. Now, you've learned in 351 that ethoxide isn't a particularly good leaving group, but the comparison we want to make is between ethoxide here after it has left and the negatively charged oxygen in the tetrahedral intermediate. In this case, we're asking, are they of similar reactivity, similar stability? And if so, then this step should be reasonable. So remember, a negatively charged oxygen can kick off another negatively charged oxygen leaving group. Now, this ultimately is our Claisen product. Unlike the aldol, it's not a beta hydroxy carbonyl compound. Instead, it's a beta keto ester because we have a ketone on the carbon that's beta to the ester. In practice, and so I'm fine, actually, if you want to stop the mechanism here, though your book points out something that happens, and it actually explains why this reaction is irreversible. So keep in mind, and I will just show you this for your enrichment, you wouldn't have to show this mechanism, but keep in mind that a proton alpha to 2 carbonyls has a unusually low pKa of about 13. So as soon as negatively charged ethoxide leaves, likely the first thing that happens is an extremely downhill, irreversible type step under these conditions where we remove the alpha proton and form the enolate. And then it's only upon subsequent aqueous workup that we are able to reprotonate our stable enolate to give us our beta keto ester. And essentially, we do this by adding water and adjusting the pH until it's lower than the pKa for this proton. So some ask, why do we deprotonate, then reprotonate again? That's simply a practical issue reflecting the fact that when ethoxide leaves in this step, it's a good enough base to remove that proton that's alpha to 2 carbonyls. But in terms of, show me the mechanism, you could stop here. All right. So we're going to have the same issues with trying to do a Claisen reaction between 2 different issues. Hold on. I was trying to write and talk at the same time, which is difficult. We're going to have the same issues trying to run the Claisen reaction between 2 different esters as we did for the aldol reaction. That is, having to choose who gets to be the enolate and who gets attacked. And we're going to have the possibility for many different self versus cross Claisen products, just as we had many self versus crossed aldol products. And so our typical solution is going to be to use a partner that doesn't have any alpha protons. So use this ester and then use another ester that does have alpha protons. This one gets to be the enolate, and so the product of that reaction can only be this. You can't get any of the self-Claisen product of this ester because there's no alpha protons there. I will point out, though, that you would still worry about the self-Claisen of your ester that does have alpha protons. And so I'm not sure how well this works, but we're going to pretend like it does. Though in reality, if you ever get in the lab and do this, you may discover that it's more complicated than that, and you'll know why, because it may be difficult to control whether the enolate we form here will react with another molecule of our ester in orange versus the purple one. Yeah?
So for this class, we don't need to worry about the self product.
You could show, if predict the products here, you could show this as the only product. Yeah. Okay, others? One other solution is to use, this is sort of, again, pretend, this is sort of cheating. One other solution is to use a really reactive ester as your electrophile. So you can make this particular ester that has both the ethoxy and the chloro there. This is sort of a mix between an ester and an acid chloride. So if you use sodium ethoxide, you're going to remove this proton to give you the enolate, which I'm going to skip over that. You attack the carbonyl carbon to get you a tetrahedral intermediate, and then this intermediate, and this will happen, and you won't even need to worry. We weren't worrying about it anyway, but you really won't need to worry about the self-Claisen product because this is so reactive that the enolate will preferentially react with the chloro partner versus itself. The tetrahedral intermediate we get from that looks like this, and now we have a choice because we have not only the ethoxy leaving group but also the chloro leaving group. Chloro's better, as you learned in 351, so electrons will kick down and the best leaving group leaves, and then our product is still a beta keto type ester, only you've got esters on both sides. We've seen this molecule before. This is actually called diethyl malonate, and we used it in the previous chapter to do enolate alkylation reactions. So probably the text will have you needing to do this reaction to get here, and then in a synthesis use what we learned in chapter 17 to make some molecule. So it might be, and remember, enolate alkylation is just removing this proton and then attaching an alkyl group via an SN2 reaction. So it might be a good idea for you to think about how you would use the reactions we've done so far to get from these simple starting materials to the following product. You can use any reagents you want. But as a hint, you're going to need to go through this, and then you're going to need to remember what we did with this malonate molecule in the previous chapter. I'll go ahead and fill in the notes when I post them. I'll fill in the solution, but don't peek. You should give this a try ahead of time because this is a nice synthetic series that really tests your understanding of the reactions. Okay, other questions so far? Yeah.
So would we use this method more than the first method you talked about because of the...
Will we use this method more than this one? Well, it will depend on what we want. This method works, but what if you don't want the beta diester? What if you want to have an alkyl group there? Then you're sort of limited to this one. Yeah. Okay. Others? As with the Aldol reaction, we can do the intramolecular version of the Claisen. Your text gives this a name, the Dieckmann condensation. We won't worry about that name. I told your classmates in the first hour that named reactions are sort of ways that organic chemists try to impress people at parties. Like if you can rattle off the name of some dead guy who invented the reaction and then act like everybody knows what you're talking about, even if they don't, and then you feel good because they feel stupid. It's a really bad way to live your life, right? But that's what sometimes happens. So if you want to know more about reaction names to try to impress people at parties, like I told your classmates, you can come talk to me. But if you're coming to me for party advice, you probably got bigger issues than OChem. So I would just say... all right, so the intramolecular version of the Claisen, what we're going to do is draw a molecule that has esters on either end. And let's see, I'm not sure if we, 1, 2, 3, 4, 5, 6, sure, that works. This ester is symmetrical, so we don't actually have to worry about which alpha carbon should be removed and which carbonyl carbon should get attacked. So let's see. if we use sodium ethoxide, again, why are we using this as our base instead of hydroxide? We're matching the nucleophile / base such that if this were to attack the carbonyl carbon, you'd get a tetrahedral intermediate like this where you've got two of the same thing attached to that carbon. Either one can get kicked off and that takes you back to starting material. So this matching the identity of the ester here with whatever base you're using is a way to make the competing substitution reaction where you attack the carbonyl carbon to make it inconsequential, okay? So if you weren't worried about that, that's fine. If you were worried about it, don't worry about it because we've taken care of it. So your base is going to remove the alpha proton, and that's going to generate the following enolate. And at this stage, it's useful to number your carbons. I tried to make some joke in the first hour that fell flat about counting your many carbons and naming them one by one, and decided that if I was going to use it during this hour, I would make fun of it, and then I would feel okay. It's sad when dad jokes fall flat. 1, 2, 3, 4, 5, 6. My son Dallin, the 14-year-old's favorite response to dad jokes is, "Oh, Dad, I've had root canals funnier than that." He actually has had a root canal over the summer. We're trying to get him to brush his dang teeth. Decisions have consequences. Wow. All right, so here's how you determine what the product is. Count the carbons that are between, count the alpha carbon and the carbonyl carbon, and all the carbons in between. 1, 2, 3, 4, 5, 6. You're going to make a 6-membered ring. Draw the hexagon, number the atoms 1 through 6, and then come back here to determine what's on each atom. Carbon 1, the alpha carbon, is attached to this ester, so that's why I put that there. Carbon 6 should have the negatively charged oxygen of our tetrahedral intermediate and the ethoxy group, and the new bond we made is between carbons 1 and 6. Then we have electrons on that tetrahedral intermediate kick down and kick off the ethoxy group. And we'll show this as the product. Recognize, though, that probably the ethoxide removes the proton from the beta keto ester, but we're going to stop there in terms of showing the mechanism, and that will be our product. Okay? So an easy way to make a 6-membered ring. It's not, don't think of it as a new reaction because we already did this with the Aldol reaction. It's just a intramolecular version of the Claisen reaction. Yeah.
So when we're counting, we're also including the carbon bonds too.
Yeah, we're including the alpha carbon and the carbonyl carbon because this arrow signifies the new bond that we form. So that arrow establishes this connection. Okay, others? All right. So, go ahead.
We take this further and do hydrolysis and decarboxylation just to form that single.
Could you take this further, do hydrolysis of the ester and decarboxylation just to get this ketone? Yeah, you could. Yep. Good. And in fact, hydrolysis and decarboxylation is going to be essential to get to this product. Yeah. Notice this is not the intramolecular version of the Claisen. This is the Claisen step. Then to get from here to here, you need to do some alkylation followed by hydrolysis and decarboxylation. Okay, so far with the new stuff we've talked about, I feel like if you're seeing the patterns of reactivity, probably you should just be sort of like, this is just more of the same. It's not too new, not too impressive. One thing that will help you is to be looking at products and noticing the structural patterns, right? Aldol gives you beta hydroxycarbonyl or alpha beta unsaturated carbonyl. Claisen gives you beta keto ester. Those are the products of all the reactions we've done today, beta keto esters. So now I want to show you a biological example of the Claisen reaction. And instead of esters, this reaction is going to involve a thioester. A thioester is like an ester except for the sulfur instead of the oxygen. If you think about the leaving group on the thioester versus the leaving group on the ester, it turns out that it's a better leaving group on the thioester, and you can tell this simply by comparing pKa's of the conjugate acids of the leaving groups. In the case of the thiol, it's 8, but for the alcohol, it's 16. So having the sulfur leave is much more favorable than having OR minus leave. So thioesters are more reactive than esters. Nature will use thioesters when it wants to do nucleophilic acyl substitution chemistry. Basically, nature will use this instead of an acid chloride or an anhydride, and the reason for that is that acid chlorides and anhydrides are just too reactive. It would kill us. So instead we use the thioester, which is stable in water and can last quite a long time, but it's still more reactive than the ester, and it's useful. And a thioester that we will encounter a lot as we deal with metabolism is Acetyl-Coa. This is the acetyl portion, and then CoA is just a large group, quite long, and we could draw it out, but we're going to ignore it anyway, so we're just going to abbreviate it. But the key is it's a thioester. This is a sulfur bonded to a carbonyl carbon. So what does nature do? Well, first, and what we're talking about is going to be in the context of fatty acid synthesis. And so what is a fatty acid? Well, it's a carboxylic acid that has a long chain of hydrocarbons. And interestingly enough, those come in 2 carbon units. So this is a 14 carbon long fatty acid. In nature, a lot of them are 16 or 18 carbons long. And these are involved in lipids. By the way, getting these from the fats and oils via the saponification reaction was how we make soap. So what we're going to talk about today is a key step in how nature makes the fatty acid to begin with. And each of these 2 carbon units comes from acetyl-CoA. So how does this work? Well, first, nature takes a different thiol and does a reaction that was on question 1 of the exam, where this thiol attacks to give a tetrahedral intermediate, and then the CoA thiol leaves. So we basically transfer the acetyl unit onto the acyl carrier protein. And this is like a crane. This acyl carrier protein is this long arm that will deliver this acetyl unit exactly where it needs to go in the fatty acid synthase, which is a multi-enzyme complex. It's kind of cool that nature uses sort of a crane to deliver the right reagent to the right spot. Second, if this is a Claisen reaction, we need an enolate. And the enolate we get, you would think that nature could take this unit and just remove a proton and give you the enolate, and that seems reasonable. But instead, for reasons I'm not sure I understand, nature uses what we're going to call a masked enolate. What do I mean by that? Well, it's going to use this 3 carbon unit, and this is called malonyl CoA, or a malonyl thioester. Notice it is a beta keto acid, which is primed for decarboxylation. And remember that decarboxylation happens because when these electrons kick down and create a new pi bond, the electrons in the bond between carbonyl carbon and alpha carbon can go onto the alpha carbon where they're stabilized by resonance. And that gives you an enolate. So malonyl-CoA is ultimately derived from acetyl-CoA. Nature tacks on this CO2 group to have this molecule primed and ready to become an enolate. One reason actually why this might happen is simply to take care of the thermodynamics. Do you remember that enolate formation is uphill in energy? And the pKa of the alpha proton is such that you'd only form a very small amount, even with hydroxide as base. Your blood's pH 7, right? And so it's probably can be challenging to make the enolate under those conditions. But if you do it this way, you lose CO2, which is a gas, and bubbles out and dissolves in your blood, and then you exhale it. And so this step is irreversible enolate formation. Okay? So then the enolate that we form in the enzyme active site will attack the thioester. Okay, and attack of that thioester will, give you the following intermediate: negatively charged oxygen, methyl group, and then the acyl carrier protein, which is actually going to get kicked off. The thiol there is going to get kicked off as a leaving group. And then we now have a new beta keto thioester, right? And so we've taken 2 carbons from acetyl-CoA and 2 carbons from malonyl-CoA and attached them together. Now we've got two carbon units. We've gone from a chain that was 2 carbons to one that's 4. We're still not at a hydrocarbon yet. Nature needs to do a few, 3 more steps, which involve reducing the ketone, eliminating an alcohol, and then reducing an alkene. But ultimately, we end up with this 4-carbon longer thioester. And then, guess what we do? We take this, load it onto the acyl carrier protein, bring in another equivalent of malonyl-CoA, and then turn the crank another time, and that puts another 2-carbon unit on it. And then this goes on and on and on until we get to the appropriate size and then stops. All right, questions about that? Yeah.
You highlighted the two carbon chains in blue.
Yeah.
Where did those come from again?
The 2 carbon chains, 2 places. Let's see. Maybe I should use different colors to be more precise. We used orange for acetyl-CoA, so those are the ones that end up here and here and here. And then the next ones come from malonyl-CoA, where we decarboxylate to make this enolate. And then we get to that step, and then this one.
Yeah,
Yep. And one thing that doesn't necessarily make sense is, where does malonyl-CoA come from? I'm not showing how that gets synthesized. There is a process for making it. It comes from acetyl-CoA. So just for now, accept that this is a readily available intermediate. Okay, and humans aren't good at fixing carbon, right? We're not photosynthesizers, so it's not like CO2 that we get. It's really totally weird. Nature takes acetyl-CoA and then it does a reaction where it reacts the enolate of acetyl-CoA with CO2 to get this. But that CO2 is only temporarily there. It gets released in the next step. So carbons from CO2 don't end up in carbons in molecules that we make. We need plants to do that. Other questions? Yeah.
How was that ketone reduced again from the beta?
How is the ketone reduced? Those are steps I didn't tell you about. Nature uses NADH or maybe NADPH to reduce the ketone to an alcohol. Then you do an elimination reaction to have an alkene in between these two. I mean, I can draw the intermediates for you. This is we'll get to that later, but for now, reduce with NADH to the alcohol, then eliminate to get the alpha-beta unsaturated carbonyl compound, and then you use FADH2 to reduce that, delivering a hydride to the beta carbon to get to this one. Yeah, we'll talk about those steps in the future, but there are subunits of the fatty acid synthase that catalyze each of those reactions, and the carrier protein moves things around to get to each subunit. All right. Yeah.
Talk about rewriting out onto that ACP.
Uh-huh.
Are we replacing the CoA group with ACP, or are we just doing a Enolate attack?
Ultimately, let's see. This group would need to get loaded onto the acyl carrier protein so that another equivalent of malonyl-CoA can come in and attack. Yeah.
Sorry, I'm a little confused where we get the, is that the masked enolate in the middle there?
Yeah.
Okay. How do we get to there again?
How do we get here? You don't need to, I mean, there is an answer to that, but not one you need to worry about for this class. Nature makes it from acetyl-CoA and CO2. Yeah. Yep. Okay. Others? Okay, so here's the part where people got hostile. That's when I introduced this next reaction. So just get ready. And it's okay. You won't hurt my feelings if you're hostile. I have teenagers, right? So hostility is just what I'm used to. And don't feel bad for me. I'm the one who writes the tests, and you're the ones who have to take them. So some hostility is expected. We're going to talk now about... Preach, brother. We're going to talk about conjugate addition. You've encountered this before when you've had an alpha-beta unsaturated carbonyl compound. We talked about how cuprates, such as this one, maybe phenyl cuprate, will, because of their unique structure, deliver the nucleophile to the beta carbon rather than to the carbonyl carbon. The molecular orbital explanation for this is that there is LUMO on the beta carbon because of conjugation. The other explanation is that the nucleophile can be delivered to the beta carbon because when you break this bond, you can move those electrons onto the alpha carbon where they are stabilized via resonance. And then we, in aqueous workup, pick up a proton from some source, probably water, and that gives us the product where we have added a nucleophile to the beta carbon. So in preparation for the most recent exam, you needed to be able to see that if I have a nucleophile on a carbon beta to a ketone, I could have made that via a conjugate addition or a 1,4 addition reaction. The reaction we introduce now is very similar. It's called the Michael reaction, and actually chemists now call most conjugate addition reactions Michael reactions, even though I think originally the Michael reaction referred to using enolates as nucleophiles. So here's an alpha-beta unsaturated carbonyl compound. Let's just use this aldehyde. And then let's keep things simple and use this aldehyde as our starting material. In the presence of hydroxide, the only acidic alpha proton I have is here. There is one here, but it's held orthogonal perpendicular to the pi system. It can't be, if you remove this proton, it can't be delocalized by resonance. So this proton is not acidic, which is why I'm ignoring it. You use hydroxide to remove a proton from the alpha carbon of this aldehyde. That'll generate the enolate, which you can draw like this. And then we're going to have that enolate attack the beta carbon of this alpha-beta unsaturated carbonyl compound. Now, part of the problem here is that, in terms of confusion, is that we've had enolates attack carbonyl carbons before as well. So how do you know whether it's going to attack the carbonyl carbon or the beta carbon? And the answer is, for the most part, I'm going to explore your understanding of the Michael reaction not by asking you to predict the products per se, but rather to show the mechanism. So if you can recognize a Michael product and push arrows to get to it, that'll be sufficient. That being said, I think you can use as a good rule of thumb that if one of your reactive partners is an alpha-beta unsaturated carbonyl compound, probably the enolate will attack that at the beta carbon. So if you've got the alpha-beta unsaturated carbonyl compound, probably you're going to need to do a Michael reaction. The way that works is enolate attacks the beta carbon, same as we did above. Really, it's dumping electron density into the LUMO and then breaking one of the two pi bonds. The electrons in the pi bond go on to the alpha carbon where they're stabilized by resonance. So here's my aldehyde. Here is the new bond that I made. Maybe, hold on, I want to keep things sort of the same orientation. So here is where the negative charge goes. Here is the new bond that I made, and here is my aldehyde. And then, in a subsequent step, electrons can, on the enolate, can pick up a proton, probably from water, and that will give us this product. Sorry, along the way, a hydrogen became a methyl group. Had to fix that. All right. So there's the product of our Michael reaction. If you want to recognize products of Michael reactions, you can do this in a couple of ways. Start with the carbonyl, alpha carbon, beta carbon, gamma carbon. But so if the gamma carbon is also alpha to another carbonyl, then you could have made that via the Michael reaction. The other way, which is simpler, is just to number 1, 2, 3, 4, and 5. A 1,5-dicarbonyl is a Michael product. If you have a 1,5-dicarbonyl, you could have made that via the Michael reaction. All right, questions about that? Yes?
Would you ever, could a Michael product be longer than that, potentially, where it would make it, you could then do a Claisen?
Could a Michael reaction be longer than that? That will depend on what these groups are on either side of my enolate and then my alpha-beta unsaturated carbonyl compound. So yes, though the bonds that form are going to be as shown here for this simple example. Yeah, what else?
Why doesn't the negative charge on the alpha carbon in the third step there resonate up to be on the oxygen so there's more to the alcohol instead?
Okay, why doesn't the negative charge, because you could draw a resonance structure that looks like this, and the negative charge would be on the oxygen. Why don't we form a bond there with hydrogen to make the enol product? That happens, and in fact, that's actually what happens first, because it's faster to protonate on oxygen than on carbon. So you actually make the enol first, but the ketone is more, or rather the aldehyde is more stable than the enol. So what will happen over time is we'll remove the proton and put it back on the alpha carbon to get the more stable ketone product. But yeah, that does form, and it just This is the enol form, and it's in equilibrium with the keto, or yeah, the keto form, but the keto form is more stable. So I often, just to save myself time, protonate on the alpha carbon and go straight there, even though this is more realistic. Okay, others? Yeah.
Could you possibly, so like, I think you kind of talked about it a little bit here, but instead of as aldehydes, it was S or something, could you then continue to react that product?
So if we had things here, would there be the potential for subsequent reactions? Yes, and that's actually where we're going. So this is where I think the subdued hostility sort of broke into open hostility. Because you can actually take the product of a Michael reaction, and if there were carbons here, we could actually do an intramolecular aldol to give us a 6-membered ring, which you hate, right? You should hate them less than 3-membered rings because they're more stable than 3-membered rings. But what I'm going to show you now is the combination of a Michael reaction and an intramolecular aldol. Okay? Because organic chemists like to try to impress people at parties, this is called Robinson annulation, after the Nobel laureate that discovered it. Annulation is a fancy word for making a ring. It comes from the same Latin root that we use for like our calendar, our annual whatever is the year. But also Spanish speakers, I think the word for ring is anillo, so it's the same sort of idea. But you don't need to think of it as a separate thing. It is simply a Michael reaction plus an intramolecular aldol. So I'm going to keep the players fairly simple for our first reaction. Here's an alpha-beta unsaturated carbonyl compound. Here's a ketone. We're going to make the enolate. This reaction is done using OH-. I'm not going to show you the making of the enolate from the starting ketone because I think you can do that without my help. You're going to have the enolate attack the beta carbon. That's the Michael step. And your product is going to look like this. Here is the new bond we just barely made. On that beta carbon that we've attacked are 2 methyl groups, then the alpha carbon, then the carbonyl carbon, and our alpha carbon should be negatively charged at this stage. Notice that we have this pattern of the Michael product, 1, 2, 3, 4, 5. It's a 1,5 dicarbonyl. And we will pick up a proton from water at that stage to give us the Michael product. I chose this example deliberately because, let's see, carbonyl, alpha, beta, gamma, which is also alpha to that one. Because this is a symmetrical molecule. It's a 1,5 dicarbonyl compound, but at this stage we don't need to worry about who attacks whom, because really these 2 carbonyls are equivalent, as are these 2 alpha carbons on the end. If we removed blue alpha proton and had it attack red carbonyl carbon, that would be a 1, 2, 3, 4-membered ring. If instead we removed this other orange alpha proton that was on this portion of our alpha-beta unsaturated carbonyl compound, then we'll generate a new enolate that we can use in an intramolecular aldol to make a 6-membered ring. So we'll draw that enolate. Okay, and then this is not new. You've done this before. Enolate attacks a ketone in the same molecule. They are 6 atoms apart. This is the new bond that we've made, so we're going to draw as our product a hexagon. Then you number the atoms of the ring, 1, 2, 3, 4, 5, 6. And you come back up here and remind yourself that there should be a ketone on carbon 2. Carbon 4 should have 2 methyl groups. Carbon 6 should be bonded to carbon 1. That's where this comes from. And then on carbon 6, we should have both a methyl group and a negatively charged oxygen. Then that negatively charged oxygen will pick up a proton from water to give you the beta hydroxycarbonyl compound. And then usually in the context of a 6-membered ring, there will be the subsequent elimination or dehydration reaction to give you the alpha-beta unsaturated carbonyl compound. And in the Robinson annulation, Smith never shows you a beta hydroxycarbonyl compound as a product. It's always the alpha-beta unsaturated carbonyl compound. Okay? So that is the worst, I think, longest mechanism that comes from this class. We made it a little simpler by skipping a few proton transfer steps. I didn't show you this protonation. I can do that actually. Whoop-de-doo. Elimination is going to involve removing the alpha proton to get an enolate, and then electrons from that enolate kick down and kick off the OH group. That's the Robinson annulation. We've got just a bit more to do on that next time in terms of recognizing the product of a Robinson annulation and planning a synthesis, and then we'll move on to benzene.